Okay, great. So we found the adapter, which is good. So the folks who are not with us will be able to watch it, the video. So today we're going to do current mirrors. That's kind of moving a little bit away for a moment from the amplifiers and frequency analysis. And then later, as you'll see, we'll use these same current mirrors to kind of add them as active loads to the amplifiers and to eliminate kind of the resistors sit around the circuits. And so it would be important to analyze them just standalone first. So we're going to start with some simple or simplest mirrors. And one example would be, for example, this. We have some current that we want to plug into the FET, and then on the other side we have, so we'll call these two M1 and M2, for example. And so here will be the output current, and so we're plugging in the IN into this FET. It reacts because it's diode connected by kind of developing a VGS that corresponds to this amount of current. And that VGS is shared between these two, so it sets the value of the current for the output transistor, assuming that this voltage is something reasonable, keeps it into forward in the saturation region. So with this, we assume that M2 is in saturation. Okay, so we're going to label this as sort of our V out, and then this will be our input voltage here. And so let's take a look and analyze the circuit a little bit in a few scenarios. So the first always is saying, look, let's do sort of the idealized version where there is no channel length modulation effect. And that means that my current is independent of the VDS voltage. And with that, okay, since we have that VGS1 equals VGS2, then if these two transistors have the same size, then ID1 will be equal to ID2 and equal to I in. And from here, I out will be equal to I in. So I'm showing here DC currents, right? At low frequency, you will have the same thing. So I can kind of add here small signal and say here that there is a small signal output current, right? And again, at low frequency, small signals, my I out will be equal to I in. Now, at high frequency, I out is not going to be equal to I in because there's a lot of different capacitor paths through which the currents can leak out, right? So not all the current will be going through this transistor, through the drain, and being replicated over here through sort of the VGS factor, right? Okay. So if WL over L1 is different than WL over 2, so we're sort of just going through to see what happens. We still have the VGS that is shared between the two transistors, so we can write the two equations So VGS1 is equal to VGS2, and that is equal to V threshold plus the overdrive component that we know on this side is caused by I in, right? So that would be 2 times I in over K prime W over L1. Okay, so if we now write the expression for the output current, that will be K prime 2 WL2 times VGS2 minus V threshold square. Now, I can rewrite this as 2 times, and then replace this VGS1 into the equation. So I'll just get VTH is canceled out, and then the square of the root. So I'll get 2I in over K prime W over L1. So from here, you see that the I out is really just the ratio of the sizes times I in. So it's now a multiplicative current mirror where I can use the difference in sizes of M2 and M1 in order to get IO to be some multiplying factor of I in. Okay. Oops. Okay, we started at the bottom. I'll shift it. So now, just in terms of understanding a more realistic scenario, let's assume that lambda is actually different than 0. That means that we now have the channel length modulation effect back, and say what happens if W over L1 equals W over L2. So if we draw the I out as a function of the V out, which is the same as VDS2. If we have our transistor curve, and then there will be some slope here that crosses at minus VA voltage, which will be 1 over lambda. Right? So we know that this is the slope, and I can say, okay, here is VDS1. So that VDS1 is fixed by I in because VDS1 equals VGS1. Okay? And that will give me I in here. Now, if my VDS2 is larger, I'll need to, so this curve here is VGS1. That's the curve that's dictated by, or sorry, VGS2. VGS2, but that equals VGS1. So if I'm changing the output voltage, I really am going around this curve. Okay? So if VDS2 or V out is equal to VDS1, then I'm at this same point. So then truly, so only at this point, IO is equal to I in. But anywhere else, I have an error. Right? And that error is kind of proportional to this slope over here. And we know that the slope is the slope is proportional to our ID over VA or lambda, right? So ID. Okay. So if I am somewhere over here, then the delta between the two will be delta I, and this will be the true I out over at this point over here. So let's take a look at what that, how to quantify that a little bit more. So at DC, we're going to have that I in is K prime 2 double over L1 times minus VTH square 1 plus lambda VDS1. And then I have that the output is proportional to W over L2. Now, VGS2 minus VTH squared 1 plus lambda VDS2. Now, this one is really VGS1 because they still share the VGS. And if I divide these two down, I'll get that I out over I in equals over W arrow 1 times, and now I have this gain error factor. And that will be 1 plus lambda VDS1 over 1 plus lambda VDS2. Now, since this is a small quantity, so I'll just represent this as 1 plus lambda VDS1 times 1 plus lambda VDS2 to the minus 1. And because this is a small quantity, I can rewrite this as 1 minus lambda VDS2. Oh, did I? Yes, sorry. Thanks. This is VDS2, this is VDS1. And then VDS1. Okay, so I can represent this 1 plus lambda VDS1 to the minus 1 as a difference of 1 minus lambda VDS1. And then when I multiply, I'll just get rid of the second order, which is lambda squared, because that's too small. So I will get 1 plus lambda VDS2 minus VDS1. Okay, so my I naught equals W over L2 over W over L1 I in times 1 plus lambda VDS2 minus VDS1. Okay. So this piece over here we call gain error. Okay. And for all these different topologies, or we'll call it systematic. And for all these topologies, we will be finding essentially what the systematic gain error is. And you see that it's a difference generically of the drain voltages of the devices, or the device which receives the reference current and the device that's supposed to reproduce that current out. And in a bunch of different topologies, we'll be trying to somehow hide that device that reproduces the current and then equalize the drain source voltages so that we can minimize this error. A number of topologies will be achieving this, but then having some other issues along the way. Okay. Now, in terms of the small signal model, if you take a look at how the circuit looks like, so again, there's I in. Okay, let me make this a MOSFET more than a bipolar. So this over here is going to be what? When I have a diode connected transistor, what it ends up being? What is this? What's the small signal model of a diode connected transistor? Yes, and what's the value? Okay, so it'll be 1 over GM. We are pretending that this I in also has the I in like a small component, right? And so here we're going to get some I in. And then on the other side, we have, so this will be our VGS1 equals VGS2. And then here we have GM VGS2. And then we have RO2. And this is IO. And we essentially get VO. Okay, so if I look at the output current, so that output current is GM2 times VGS2 plus VO over RO2. So my IO is GM2, and VGS2 is I in 1 over GM1. And then plus VO over RO2. So if these two transistors are the same, then GMs will cancel out. If they're not, then I still have this W, this ratio of the sizes that will determine the multiplication factor, right? So this will be WL over 2 over WL over 1, because everything else will cancel out. So I do preserve that multiplication factor, but I have this additional modulation, so to speak, where now my output voltage affects the current, right? And you see an interesting thing here. The larger the output, so RO2 in this case is the output impedance, or at these small low frequencies, it's output resistance of M2, right? And the larger this number, the smaller this effect, right? That VO over RO2 is going to change the current. So this RO2 in this case will be the output impedance of our current source. And we know that the ideal current source has infinite impedance, right? So however you change that voltage across it, there is no change in current, right? So our goal will be to construct sources where we have something where we can build R out that is much larger than R naught. And that way we're going to get a better current source with less gain error. Okay. So there's some practical notes for building these current multipliers. And one of those is, of course, picking right W over L. So if I'm supposed to do some multiplication, what do? I pick larger. In order to have WL2 greater than W over L1, what do? Do I change the size? Do I change the channel, the length of the channel? What do you think? So I guess one scenario is to say that, okay, well, W2 will be some K time or M times, let's call it M times W1, and I keep L1 equals L2, right? Is that a good suggestion?
Do you want to avoid channel length modulation?
Okay, so I think the point here is that channel is being affected by things, right? For example, like XD, right, which is the depletion. Even if we say XD is 0, we still have LD, which is kind of how much the source drain get underneath the drawn gate length, right? So my L effective will be L minus 2LD minus XD, and in different cases, this for different starting lengths, the L effective will be different. Even if the starting lengths are proportional, the L effective is not going to be proportional, right? So for example, this is actually a reasonably good strategy, right? If we had, for example, the L1 equals 1 micron and L2 equals 2 micron and LD equals, let's say, 0.1 micron, W, for example, is 200 micron, then you would have one ratio would be 200 over 1 minus 0.1, and another would be 200 over 2 minus 0.1, right? Obviously, this is not essentially the case and where this is integer, right?
B minus 0.2.
So, sorry, yes, you're right, 0.2. We should say also that xd, we assume 0, okay? Okay, so now we've lost our ratio, okay, here. And so the suggestion was here to say, well, okay, let's not use, let's use the same else. So what we have then is, we can say that W1 equals 2W, or W2 is 2W1. L1 equals L2. And then nominally, we should be able to get that W over L2 is 2 times W over L1, even effective, right? However, the problem is when you actually do fabrication, when you look at the transistor, if this is my L and this is my W, and then I build one that is twice that much. Okay, something crazy is going on. The way lithography happens, you actually have sort of the active area underneath that is shrunk also from the W side. Because they're sort of the edge effects of forming the channel in the fields. And so what happens is that these are, again, just like LD, sort of fixed quantities on each side. So that, again, I have W 1 minus 2 delta here, and then I have 2 W1 minus 2 delta. Again, this is not the case, right? Okay. So what's the best strategy? I can't double the length. I can't double the width. I lose. So, but what can I do? You're still not going to, you still have this problem of fixed offset, right? So however, so fixed offset on something, you sort of lose the linear proportion, right? So you can't escape this. So anybody has any ideas? You can play, but threshold is a very expensive step. You have to dope differently and stuff. You're a designer. You're supposed to take care of this, not the fab. Change what? I didn't. That's still process. You're given a process, and you need to just. You can only manipulate W's and L's. That's all, right? Even L in modern processes, and even W's in modern processes, you won't be able to do it. But what can you do? Yeah. Yeah. See, this is great. So the suggestion is keep this one like this, and then just use that same thing twice. Okay, and then just connect them together, right? Now you've got yourself exactly 2x the size, right? Okay, so that device would look something like, in your schematics, if you drew it, you would essentially do this, and then say, okay, I have one, and then I have another one over here. and then they're connected together. Right? So all of these have some fixed W over L. In fact, in modern design, you actually do a lot of these on the sides as well, so that only the ones in the middle are kind of not stressed and well matched. And so that's how you ensure that the multiplication here is exactly some integer amount. Okay. Okay. So we've covered the simple cases. Now we're going to move to sort of a bit more complex topology, which is Wilson. By the way, all these have bipolar equivalents, and you just have to worry about sort of the base current. So you can take a look in the book. I can't cover both topologies, but very similar principles apply with some minor differences that we'll see that in MOSFETs we can actually keep increasing the output resistance by doing cascoding or tricks like in Wilson. These things will be a little bit harder to do in the bipolars. So some topologies will be restricted in how much you can grow the output impedance because of the beta. In MOSFETs, beta is kind of infinite, so you can keep going. And in, for example, if you do double, triple cascodes, like we're going to show next week, you can keep increasing your output impedance. While in bipolars, you can't, because you're always limited by the beta factor between the base and the collector current. Okay. So those are some minor differences you can read about, but pretty much topologies and principles are very similar. So the main point of the Wilson is to try to boost the output impedance, and so we're going to see how it does that. So let's label these M1. 2, 3. There will be I out here. I'm going to be looking also at R out, and we're going to label this as VO, and then again, this voltage will be our VN. So let's take a look at the little experiment here. If I increase V out, what happens with I naught? Does it increase or decrease? It increases because the source has some finite output impedance, right? So if the voltage increases on any given R, your current also increases, right? So I'm going to say, okay, knowing that this has some finite output impedance, if I increase the output voltage, likely if there's no other regulation mechanism, this I is also going to increase, right? So if I increases, that means that this VGS also increases because this is diode connected, right? So it maps that increase in I naught to this guy over here. So then I3 will increase because its VGS voltage increases. If I3 increases, it pulls this node more down, right? So then Vin decreases. And if Vin decreases, it basically pulls this gate down. And then what happens with I naught? So I naught goes down. So what is this called? Yeah, so this is negative feedback. So this is how Wilson essentially has larger output impedance. Okay? because it manifests itself in kind of dampening the changes in I out as a function of the output voltage. So whatever output voltage is trying to do, this feedback is trying to stabilize I naught to be kind of the original value. Okay? So let's take a look at the small signal circuit, and you'll be able to calculate actually what is the output impedance. So if we start from M1, we have GM1 times VGS1. We have RO1, and then we're going to apply I test and measure V test. And then at the bottom of this, what do we have? What is M2? Small signal. Yeah, resistor 1 over GM2. I'm not putting RO2 because it's small, so I don't want to sort of carry it along. And then this is VGS2, and that equals to VGS3. And then here on the VGS3 side, I have GM3 VGS3, and then I have RO3. And then the voltage that's developed here is VGS1. Right, so this voltage over here controls this current source over here. So if we go and write a few things, so VGS3 over here is minus GM, sorry, it's not this. We're going to say that IT flows this way and then also flows over here. So VGS3 is the same as VGS2 and is IT over GM2. Okay. So we have also that VGS1 is minus GM3 RO3 times VGS3, which is IT over GM2. And then we can write up for VT. So VT is this IT over GM2. That's this. Plus RO1 times whatever current is flowing through that. And that current is I test minus GM1 times VGS1 times minus GM3 RO3 IT over GM2. Now you start seeing I'm starting to get some multiplication of R naught over here. So I'm going to have my VT equals IT over GM2 plus RO1 IT minus, or I'm going to do plus now, GM1 times GM3 over GM2 times RO3 times IT. So I can now say my R out is VT over I test, and that is 1 over GM2, which is small, plus RO1 plus this factor, GM1, GM3 over GM2, RO1, RO3. Okay, this is the important piece. Okay. If these transistors have the same size, so all the GMs will be the same and R naughts will be the same. So this is approximately GM times RO square. So this is the big deal, right? Now I've taken R naught from the simple structure that we've done previously, and with this negative feedback in Wilson, I've multiplied it by the intrinsic gain of the transistor, right? So this is the gain. So I've got, just because of this feedback now I have a bigger output impedance. Okay. Now another thing that is worthwhile looking at here, and let me just redraw the structure a little bit. So we can see better. Another thing, so this is small signal stuff, but one thing that's interesting to us is also how low can the input V in here and the output voltage, how low can these go? And the reason is that, especially in modern processes, I have a finite supply, a finite difference between this, which is, let's say, VDD, and ground. And I want to be able, especially over here, to put a lot of different circuitry. And all that circuitry has to be in saturation. And so I need to guarantee a certain VDS for all the circuits that end up being over here. So I want VO as small as possible. So let's see what's the smallest possible VO for this. Anybody have any ideas? So we're going to look at VO min. What's the smallest possible VO so that both M1 and M2 are going to be in saturation? V overdrive? The V overdrive will be part of it, but there's a little bit more. Which way would you go about calculating VO? How do you get from ground all the way to V0? Do you go through M2 or through M3? You go through M3, you just get VGS. You don't know what VGD is, right? If you go through M2, this is VGS. Plus, I have another VGS. And then I have minus VGD1, right? And so if I look at this, this is some V threshold plus V overdrive. V overdrive is just how much above threshold I am, so that's proportional to the square root of the current, right? And that's dictated by this IN. Then here, I have, again, V threshold plus V overdrive. And then what is the largest quantity that this can be so that I minimize my VO min? In other words, how much can I lower the drain with respect to gate and still have the transistor be in saturation? So the output could be, the drain source could be VGS minus VT, right? But what's the difference of the gate to the drain, right? So just this voltage. Yeah. So this difference has to be less than VTH, or less than or equal, right? So the largest voltage I can have here is VTH. Okay. So now my minimum VO is actually VTH plus 2 V overdrive. Okay, Okay, this is something you sort of have to become skilled at, right? So you just look at this and say, okay, here I have VTH plus V overdrive. Then here I have another VTH plus V overdrive. And then I go down by VTH. So then this is 2 VTH plus V overdrive. Okay. Now, that is, so what is, in that case, what is VI min? We sort of calculated already here, right? That's this voltage between this and ground. It's this plus this VGS. So it's 2 VTH plus 2 VOV. Okay? Now, what's the systematic gain error? We know it's going to be lambda, right? Because it comes from channel length modulation. It's going to be the same exact kind of ratioing of wherever our diode transistor is, which diode connected, which sort of maps the current and serves as a reference. In this case, that's M2. And the other transistor, right? Which is the one that kind of controls the output, and that's M3. Right? So we're going to have this to be VDS2, which is this voltage over here, minus VDS3. Now, because this VDS3 also has to fit the VGS of M1, obviously these two are not the same. So this is approximately equal to, or actually not approximately, it's equal to lambda or minus lambda VGS1. Because VDS3 is VDS2 plus VGS1. Okay. So we still have some systematic error in Wilson as well, and we'll see with what topologies we can sort of get around that. So let's improve that Wilson. Okay. So now we want to attack this problem of this VGS1, right? So we want to try to modify this part of the circuit so that we can lower this VDS3 so it can better match VDS2. If that happens, then I'm nicely mirroring around the same current. Does anybody have an idea how to do that? Well, I'm drawing, so you can make suggestions. How do I take this voltage and I push it down by a VGS? Okay, so the idea is to put another MOSFET. Okay, a diode. I was just about to ask how do you bias this point, but okay, now you're biasing that point, right? And so now this diode connected FET is kind of developing a VGS to support the current just like this one over here, right? So now in this case, I've now reduced VDS3 by this VGS4, right? And so to the first order, the systematic error is now still VDS2 minus VDS3, and is equal to lambda of VGS4 minus VGS1, which is approximately 0. So this difference between 4 and 1 is way, way smaller than, and it's very close to 0. Okay. Okay, so let's do another exercise. What is V in? And what is, in this case, V out min? What is V in? How do we go about it? Can we go through M3? M2. So what's this voltage? VGS, and we represent VGS as VTH plus V overdrive, right? So this is our VGS2. Okay, next. M1. And then we're already here, and then that's the same as that, correct? So V in is 2 VTH plus 2 V overdrive. What is VO min? 1 VTH down, right, from that. So same as previously, right? Nothing changed on that side. Okay. So this is sort of a fix for Wilson, so you can have both relatively high output impedance and also low systematic gain error. We're going to do another topology, and sort of the grad students will have some kind of homework. Part of the homework is going to be on this, so pay attention. The one on the homework is even a little bit more involved, but you know the basic concepts are described here. So this one actually is probably a more familiar topology to you, because you already know that if I put two transistors like this, right, and I'm looking at the R out, you already know that this should be something like GMRO squared, right? That's from our cascode amplifier analysis, right? And so indeed, you can use that concept also here to create a current source that has the same kind of output impedance. So we're going to say this is M1, this is M2, and then I just need the biasing for this cascode, right? So the way I'm going to do the biasing is simple, just provide VGS from diode-connected devices. And so I'm going to get the mirroring at the bottom, and then this point is also going to be kind of biased by this additional device. Now notice in Wilson, we had kind of a diode connection here, not here, right? So it's a little bit of a different mechanism. But again, we're getting sort of a similar concept that we have this device. If you take this out, this is all floating over here. So really, all that's left of this device is R0, and then we have just our M2, annoying, and R01, and then we're looking at the output R out. Right? So this is going to be something approximately R01, R02. Okay, so let's take a look at the V in and V out. What is V in? Oops. V in. We can't go through M1. So V in is, yes, there's 2 VOV plus something else. 2 VTHs. What is VO min? Yeah. So it's VTH plus 2 VOV. Okay? And then what is the gain error? So I'm looking, so that's something like lambda, and then I'm looking where the mirroring is happening. So it's VDS1 minus VDS3. What's the relationship of these two voltages? This one is VTH plus VOV, right? Then I go another VTH plus VOV. Then I decrease by VTH plus VOV. So what is this voltage? It is VTH plus VOV, so it's the same, right? So this is 0. Right. So this one, again, also has systematic, very low systematic gain error.